This topic's quite a big topic. It actually covers 3 chapters in the book, or at least selected sections from them. There's quite a lot to thermal physics, and what you're going to be looking at is quite a sort of classical version of it. What becomes thermodynamics is quite usually synonymous with statistical physics. It's the physics of big numbers of particles, basically, and you look at it on a statistical scale. What we're going to do with this is look at some of the more fundamental classical ideas. So if you've studied physics at sort of level 3-ish before, you'll have probably done a bit of thermodynamics and a little bit of gas laws. So some of this stuff will be familiar, but there's a few topics in here which are, again, new to pretty much everybody. So let's just take a little look at the sections that you've got to study. So the first one is chapter 13. So really this is just looking at some of the fundamental ideas, making sure you're happy with what Kelvin and degrees C are. The first bit that's new is going to be thermal expansion. This isn't something that's really covered in any A-level syllabus specifically. So that's been new to a lot of people. So really just to draw your attention to 3 new equations. 1, 2, 3. This is talking about, for example, when you heat something up. We're not talking about in a gas laws kind of way. We're talking about in a solids way. So when you heat something up, how it changes shape. We might be aware that in really hot weather, things like railway lines can buckle if they're not built correctly, or if there's not left with enough of a space or a spacer in to allow them to expand. So this first equation here is talking about the change in length. The alpha is basically a sort of an expansion coefficient, if you like. And then again, these are unfamiliar equations, so take a little bit of time to look at them and look at what they mean. If you've got an original length, which of course is L, you've got a change in temperature and some coefficient alpha, which is particular to the substance, so that's something you have to look up, then that would give you delta L. So hopefully that equation becomes quite self-explanatory, to be perfectly frank. A is the same idea, but in terms of area. Probably slightly less useful. It depends exactly how you're going to use it. And most commonly, probably most useful would be this one, which is about change in volume. So again, there's another coefficient in there. This one is beta, and it's something which you can look up. But there is a relationship between that and the original alpha. So it's still down to being an expansion coefficient. But again, look at the logic of the equation. Although it's probably new to you, it shouldn't really be anything that you can't figure out just from reading that summary. But obviously have a little look at some of the examples in the chapter and make sure you're happy with how to use it. So then we go on to ideal gas laws. So again, if you've studied this before, maybe at physics or possibly even in chemistry, you might be familiar with some of these equations. So just a couple of things to draw your attention to. There's 2 versions of this main gas laws equation. And hopefully you can spot immediately what the difference is. It's in the N and then the constant. So K is the Boltzmann constant, which again you can look up, and N would be the number of particles. Basically, the Boltzmann constant is very, very small, and the number of particles involved in any gas is very, very large. Little n is the number of moles. So this is particles up here, and this is moles. And R is 8.31 as a constant. It's the molar gas constant. So when you use them in tandem, you're multiplying a really large number by a really small number. The 2 magnitudes kind of cancel out. Or you do it in terms of moles, in which case you're using, you'd normally only deal with in the vicinity of a mole of something, or a fraction thereof, or a couple of moles, and multiplying by 8.31. So the values you get out of this NK and NR are going to be quite similar. Obviously, if you use the wrong constant with the wrong bit of information, that can become very messy. There's a lot behind all this as well, which is well worth just sitting and exploring a little bit. So things like Avogadro's, the number of particles there are in a mole. But it's worth also delving into some of the other information that's related to this stuff, which is just remembering that the mass of a mole is the atomic mass of the gas. Or if it's a compound, then it's the kind of atomic formula mass of the compound itself. So, for example, carbon, for instance, if you've got 1 mole of carbon and it's carbon 12, then you've got 12 grams of carbon. So there's a relationship between, volume. You've got volume and density and mass in there, but there's a relationship between mass and the number of particles, or mass and the number of moles. So there's an awful lot kind of going on here that it's worth just delving into a little bit. Don't take too cursory a look at these equations. Make sure that you can do things like convert from the number of moles to the number of particles. Can you work out, for example, decimeters cubed is quite a common unit, so can you put that into meters cubed? Do you know what a decimeter is, for instance? It moves on then to a few more complicated ideas about relating the energy of something to the temperature of something. And again, it's worth just spending a little bit of time on that, perhaps more than just a quick read through, where you do make sense of these equations and potentially see if you can understand where they're really coming from. Okay? This is really a key one. Half mv squared is not a new equation, okay? But 3/8/2 kT is. And they're both the kinetic energy of a particle, so they do relate to each other. So this is talking about the root mean square speed, or the root mean square velocity of a particle. This is what the v bit means. You might sometimes see this as written as that, or something like that. Depends on what book you've got. So there's different versions of it. Again, we've got the Boltzmann constant in here, but what this is doing is relating the temperature of a gas to the it's not the mean exactly. It's the root mean square, which is a slightly more statistical idea. But what it does do is it gives you a rough idea of how fast the particles in something are travelling. Now, again, it's worthwhile just considering what that means in terms of the gas law's equation, which relates pressure, volume, and temperature. So if you think, if the temperature increases and the particles are moving faster, they're striking the sides, one, harder, because they're going faster, there's a bigger change in momentum. They are therefore applying more force with every collision, but they're also moving faster, which means the force is being applied more frequently. So this explains why we've got a relationship between temperature and pressure. And it's worthwhile, again, just having a few little thought experiments along those lines of those relationships with the ideal gas laws. In fact, speaking of the ideal gas laws, once you start to put these ideas together, don't forget that the common way of using these equations is to use them in terms of ratio and looking at changes in a gas. So if you've got a gas at a pressure, a volume, and a temperature, and it undergoes a change in temperature, a change in size, and an equivalent change in pressure, so it might expand, it might contract, whatever it is that's going on. But as long as the amount of gas stays constant, the PV divided by T value has to stay the same because it's equal to NK, or little nr, which is to do with the amount of gas. So as long as the number of moles or the number of particles doesn't change, this is always true. Now, what's also worthwhile remembering is that you can use any version of this where one of those parameters also stays constant. So if you're looking, for example, at changes in gases in terms of volume and pressure at constant temperature, then it's true to say that, provided that the temperature stays constant and the amount of gas stays constant. And there are obviously three versions of these laws. So pressure over temperature remains constant, pressure times volume remains constant, and volume over temperature remains constant. Or in other words, pressure is inversely proportional to volume, pressure is proportional to temperature, and volume is proportional to temperature, provided the third parameter stays constant and the amount of gas doesn't change. And it's worthwhile just familiarising yourself with which of these laws is which. So this first one is Boyle's law. The second one is quite often known as the pressure law, but it can be known as Gay-Lussac's law. And the volume and temperature is known as Charles' law. So remember, for each one of those, if ever you have to quote them or use them, they all have that parameter of that the other quantity. So for Boyle's law, it would be the temperature remains constant and the amount of gas remains constant. So just bear that one in mind. Okay, so that section goes on a little bit more to talk about phase changes and some more conceptual ideas. Again, it's just worth having a little look through phase diagrams, especially in reference to the triple point. Have a little look at 13.6. Again, it's nothing. There's not a huge amount of information there, but it is quite an interesting way of looking at the kind of changes in state of things. But don't get too bogged down in that, and it is only a little section, so don't concentrate too much on that. Your main concentration should really be in the first few sections. So point 1 is easy. Point 2 is just the application of those equations. It isn't complicated. Point 3 and point 4 are where it gets a little bit more tricky, and you should spend more time looking and practicing questions on that to make sure you thoroughly understand it. Okay, going on to the second chapter in this part about thermal physics and ideal gases, starts to look at heat and temperature. So this is looking at temperature change when you're heating substances up, for instance, or phase changes, so changes of state involved in, well, either the change of the energy involved in change of state, so either kind of evaporation, vaporization, or in sort of freezing and melting. So again, each of those has an equation, but these equations hopefully should be fairly familiar because they're actually GCSE. Okay, so there's again a few little bits of information in the first section there. It's a nice little intro bit just to make sure you're aware of. Where this gets to stuff that's a little bit newer, depending on exactly what you've studied. If you've done BTECs with physics elements, you might have done a little bit of this. But this talks about the heat transfers. So just one thing to draw your attention to. Hopefully you're already aware of conduction, convection, and radiation as an idea, and thinking about those in terms of what the particles actually do. But just look at Q over T as the idea of it being power. So this is the rate of energy transfer. And finally are the laws of thermodynamics. Again, I'm not going to go through these in any great amount of detail. All I'll say is it's a relatively straightforward application of things to start with. But when you get onto the Carnot cycle, you might find some of the additional sheets quite useful in just helping get your head around it. But don't try and get into the Carnot cycle until you've got a good grasp of the gas laws and the laws of thermodynamics. Because the heat engine idea and the heat pump idea basically brings all of that together.